Okay. Well, I'm glad I remembered before I got too far. Okay, so albinism involves significant reduction or absence of the production of melanin, giving affected individuals a lack of normal coloration to their skin or eyes. So we're given a condition, we're kind of told what it does, and then it moves in to tell us more about inheritance patterns. So normal melanin protein is produced by an autosomal dominant allele. So even though I don't like to use the word normal, just shorthand for people who don't have albinism. So normal is going to be dominant. Albinism results from a lack of melanin and is caused by an autosomal recessive allele. So we're told then that albinism is going to be, excuse me, a recessive trait. Here's where the information starts about what the family looks like. Before I get started then, let's go ahead and write down what we know. We know that albinism, I spelled it wrong, albinism is going to be a recessive trait. So that means you have to have that homozygous recessive to have that trait. Now, quote unquote normal, which again I don't like to use, but just shorthand, is going to be the dominant trait. So either big A little a or big A big A. Actually, let's do this right. We'll say normal is going to be homozygous dominant, and then the carrier is going to be big A little a, like we saw yesterday. Okay, so we're given a trait. It's albinism. It's recessive, which means that if you have it, you're going to be homozygous recessive. If you're quote unquote normal, that means you're homozygous dominant. And if you're a carrier, then you're going to be heterozygote. Okay, so let's get into the description of the family. Two normally pigmented parents, so that means you're going to have a mom and a dad. They are not going to be filled in because we're told that they have normal pigmentation. They have 3 kids. So then you go, oof, that was rough. Let's try it again. There you go. 1, 2, 3. The first child is a girl. Their second child is a boy, and they have normal pigmentation. Their third child, a girl, has albinism. So this child you would fill in and say, oof, and say this person is affected by albinism. There, you get it right. That girl marries a normally pigmented man, and they have 4 children. The first 3, 2 girls and a boy. So you got a girl, a boy. Oops, no, sorry. You have 2 girls and a boy. Have normal pigmentation. Their fourth child, a girl, has albinism. Now you might be thinking that we're done, but we are far from done. Now we are told that 2 people in this family tree have albinism. Albinism is a recessive trait. That means we have carriers in this family that we have to figure out. Now, first and foremost, I think you can probably start with this one right here. Now, she's going to be the most important because she is the daughter of these people and the mother of that person. So what that means then is that you have to figure out what the genotypes are. Since we know that albinism is a recessive trait, we already know what hers is, right? Hers is going to be homozygous recessive. Now, you have to work backwards and figure out what the parents are based off that information. So, we are told that they are normal pigmentation, and yet they have a child who does not have normal pigmentation. So, you draw your Punnett square. Boop, boop. And we go ahead and put the child here. Man, that's rough. I know you guys get lost when I do the whiteboard, but it's so much easier. Ooh, there we go. Okay, so she is here. Now, we are figuring out the parents, right? So if this is her alleles, you have to have parents with that recessive allele, right? You can't just have that recessive allele parent or. Now, that being said, you could have mutations. There are other things that happen, sure. But we're dealing with practice problems. We're going to say that this person has to have parents then that are heterozygotes. So we've got heterozygote parents. Heterozygote means that our parents are going to be carriers. So grandma and grandpa are carriers for this albinism trait. Okay, so we've got two heterozygotes crossing, and one of the three kids they had has albinism. You work through the other ones, and it finds out there's a 3-to-1 ratio, right? 3 of the 4 have that dominant allele, which means they're going to be, quote unquote normal pigmentation. So you have 3 of the 4 normal, 1 of the 4 affected. So 2 of them are normal, 1 of them are affected. Now this person goes off and marries somebody, and she has a kid with it. So that means we know hers. Because that was homozygous recessive, you know that this is going to be homozygous recessive. We have a little bit more information this time around, though, because we know mom's genotype. So let's go ahead and make this black. Now, we do the same thing. We know here that this child is homozygous recessive because she has the albinism gene. We know that mom is homozygous recessive. Now, dad has to have one recessive allele because, again, one of their daughters has both recessive alleles, right? This person has to get their alleles from both mom and dad. So dad has normal pigmentation, so he's going to be a carrier as well. You run through your pedigree, your Punnett square, and you find out that we have 2 homozygous recessives, which would be affected, and 2 carriers. There are no homozygous dominant kids in this family. So that means every single one of these kids is a carrier. And finally, there you go. Now, that is a completed family tree, right? We don't know 100% if these kids are going to be homozygous dominant or heterozygotes because they don't have kids of their own. So we don't super know what their genotypes are. However, we know everybody else's, right? Okay, so that is our completed pedigree. Are there any questions about how to set these things up, how to show heterozygotes? Anything? Like I said, this one's a little bit more complex. You wouldn't necessarily have to do this on the star, but it is good practice for when you have questions like this for the star. Because again, more often than not, you're going to be predicting inheritance patterns. You're going to be looking at genotypes. And in that case, you have to be able to work through the different parts of the pedigree to figure out who's who. Okay? All right, fantastic. So we're looking at non-Mendelian inheritance patterns. So again, we're gonna wrap up with pedigrees, and then we're gonna move into incomplete dominance like we talked about yesterday. And then codominance we'll talk about tomorrow. So here we have our autosomal dominant and autosomal recessive pedigrees. If I could I get a volunteer to read autosomal dominant? So these 2 bullet points down here. Can I get a volunteer to read that for me?
Autosomal dominant affected children must have at least one affected parent, and 2 affected parents can have an unaffected child.
Fantastic. Thank you so much, Denise. All right. So that is going to be our dominant inheritance pattern characteristics. Whenever you're looking at a pedigree like that, you're going to be expecting to see affected children having at least one affected parent, and 2 affected parents can have unaffected children. So how does that work? Let's go ahead and look at it. So first thing you want to do is draw a pedigree. We'll tackle number 1 first. So number 1 says affected children must have at least one affected parent. So we're dealing again, this is a dominant disorder. We're looking at both dominant and recessive, but specifically right now, this is dominant. So if you have an affected person, that affected allele is going to be capital, right? Because this is a dominant disorder. So anything you have colored in is going to have at least one dominant allele. So now we've got mom and dad, we've got two kids. Two kids have the allele, right? These two are affected because one of them has that. Now, here's where you have to think backwards. If you're dealing with an autosomal dominant disorder, that immediately means you can figure out everybody who's not affected, right? If you're dealing with a dominant disorder, in the chat box, tell me, what would the genotype be of somebody who is not affected? So one more time, if an autosomal dominant disorder is being displayed in a pedigree, what sort of genotype would you expect to see with the unaffected individuals? In the chat box, let me know. What are the unaffected individuals' genotype going to be if we're dealing with a dominant disorder? Awesome. Very good, Hugo. Very good, Josiah. Thank you, Zaria. Right? That's why you got to start thinking critically about these things. If you're dealing with a dominant disorder, at least here we're told, then you know that anybody who doesn't have it is going to have that recessive genotype. Very good. So that'll help you when you're starting to do these problems. Now, on the star, they may or may not be telling you whether or not it's dominant or recessive. For now, we're working through the different scenarios so you can figure out what to look for. So on the star, you might be told, and in that case, it's going to be a lot easier because, like I just showed you, if you're told it's dominant, every unaffected individual is going to be recessive. So we set up our Punnett square. We know that one of the parents is going to be unaffected. I'll probably make it a little bit bigger. Oop. We know that one of the parents is affected, so that means there's two possibilities, right? That person can either be this, or they can be this. Oof, it's so rough. There's the unaffected parent. The affected parent then is going to be either homozygous dominant or heterozygous. Now remember, there are no carriers in a dominant disorder, right? When we're looking at the recessive, you're going to notice that if you have that recessive allele, you can pass it down to your kids, right? But not necessarily express the trait because the trait, again, is recessive. If you're dealing with a dominant disorder, whether you're heterozygote or homozygous dominant, you are going to express that dominant trait, whether it be a mutation or a disorder or whatever. If you're homozygous dominant, heterozygote, you're going to display that. So there's no carriers in a dominant pedigree. Okay, so you run through, you've got big A little a, big A little a, big A little a, and big A little a. So you have 100% heterozygotes, or you would have this. Now again, homozygous recessive is going to be unaffected. You look at the kids, you have two affected kids, so odds are you're probably dealing with dad being homozygous dominant because both the kids have the allele. Either way, there's a chance that this person is going to produce kids with the allele too, right? These don't necessarily represent reality. Remember, the Punnett squares represent possibility, right? You're predicting things. So it is possible that the dad's either one of these. It doesn't super matter, right? Either way, the affected individuals are only going to be one genotype. You don't have any homozygous dominant genotypes. So you move down a generation to these people. Actually, let's make a different color so we don't get too confused. Let's try green. Let me go over here. We've got two parents who are, well, we actually have one parent who's heterozygote, right? Like I said, regardless of whether the dad is homozygous dominant or heterozygote, he's going to be homozygous. I'm sorry, he's going to be having heterozygote kids. So we know for sure that mom is heterozygote. Dad, again, could be anything. But because we have unaffected offspring, we have to have at least one of these, right? Any person who's not affected is going to have that genotype. So, whoop, right there. So if we got a kid who is unaffected that means that mom and dad have to have at least one recessive allele, which means that both mom and dad are going to be heterozygotes. And now, last but not least, you're looking at, let's use blue. At this one, you have two unaffected people having kids, which again is another huge advantage for you if you're looking at inheritance patterns. If you have two people who are unaffected, they are only going to have kids that are unaffected, right? That's the only genotype that you're going to see. Because again, there's no dominant allele, so that means none of the kids are going to have a dominant trait. And there you go. So that's what you would expect to see for a dominant inheritance pattern. And again, most important, no carriers. Dominant pedigrees. I guess I can make that bigger. It's worth making it bigger. There you go. Okay. Are there any questions about what I did there? Like I said, what I'm trying to show you is what you look for when you're looking for dominant or recessive in a pedigree. Dominant, I think, are the easiest because whenever you know you're dealing with a dominant disorder, all of your unaffected individuals are going to be, again, homozygous recessive. So I can make that pretty simple. Whenever you're trying to figure one of these out, I would say that you should probably do at least 3 just to make sure that you are getting the right answer. Yeah, do at least 3 pedigrees. Choose 3 different families and try and figure it out. That's the best way to get to the right answer. Okay, recessive. Can I get another volunteer to read the bullet points underneath autosomal recessive?
I can.
Thank you, Brayden.
Okay, both parents don't have to be affected, but both must at least be carriers. Heterozygous. 2 affected parents will only have affected children. This trait often skips generations. The trait will also appear more often in children of.
Very good. Thank you, Brayden. So we mentioned this the other day, how consanguinity, like I guess incest would be the not nice word to say, right? That's where you're going to see a lot of these things happening with recessive. It becomes more increased frequency with bloodlines that are related. Let's pick a purple one. How about purple? So what it tells you is that here you are dealing with carriers, right? Because we have 2 kids. We have a kid that's affected and a kid that's not affected. So if we have affected children with an autosomal recessive disease, that means that you have to be dealing with carrier parents because the recessive allele needs to come from somewhere. Now again, in real life, it's not necessarily always that clean, but for the purpose of this, let's just go ahead and say that it is. Okay, so there you go. So 3, we have our 2 carrier parents. Why can't I draw a normal square? All of my squares come out like Tim Burton style, for those of you who are Tim Burton fans. It's all at an angle. Okay, much better. All right, so we know that mom and dad are both heterozygotes. Make it bigger, make it black. So there's mom, here's dad, and it's something you've seen before, right? This is going to make what's called a 2-to-1 ratio. So for every 1 homozygous dominant, you will have 2 heterozygotes and 1 homozygous recessive. So all 3 genotypes are possible based off of this pairing. Now we have an affected individual and an unaffected individual. If you're dealing with an autosomal recessive disorder, then you know that anybody who has it is going to have the homozygous recessive. Oh wait, did I do this right? No. There we go. So in the same way, when we're dealing with the autosomal dominant, you'd assume that everybody who didn't have it was autosomal recessive. Here, if you're dealing with an autosomal recessive trait, that means that everybody who does have it is going to be homozygous recessive. So that's going to be the biggest help, I think, whenever you're dealing with these problems, is trying to figure out which one is recessive, the people who are affected or the people who are unaffected. And it might take you 2 or 3 Punnett squares to get to the answer, but it's definitely doable. Okay, so we know the kids, we know these parents. Now, it says 2 affected parents will only have affected children. So looking down here at this couple, let's go ahead and make this one red. This couple here, if we know that the affected genotype is going to be homozygous recessive, oopsie. There we go. That means that they're only going to be able to produce children who are, again, their same genotype, because there are no other alleles, right? So if there's no other alleles, that means that they're just going to produce the same thing, which again is why you see it so commonly in cosanguineous relationships. So that's the fancy way of saying incest. So you have little a, oh, you can't see it because it's white. Little a, there's dad, and of course here's mom, same thing. So if they are both homozygous recessive, that means they're only going to have kids with the same genotype, and that's it. So you have 100% of the offspring are going to be affected, which is what you notice, right? All 3 of those kids are going to be homozygous recessive. That's exactly what you see. Boop. 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 And now here, let's go one more color. Let's go blue again. Let's go with these people, right? Remember that our mom and dad in this generation were carriers, right? So if they were carriers, that means that you could be homozygous dominant, you could be heterozygote, but because this lady was unaffected, she is not going to have that one, right? So she could be either one of those. So these two people get together and they have kids. So that means if that boy has the recessive alleles, that means that you're going to have at least one recessive allele here, one recessive allele here. Because they're both unaffected, you would say that they are heterozygotes, which makes sense because we saw that right there. And there you go. You have the possibility of having the kid homozygous recessive. Okay. So both parents don't have to be affected to pass it down. They can be carriers. 2 affected parents will only have an affected offspring. So remember, it could be the other way around here with the parents. 2 affected parents could produce kids who are not affected, versus here, affected parents will produce affected children. And this trait skips generations because, of course, you have carriers, right? So even though, let's go ahead and show that with our marker, these people are unaffected, they are both carriers. Now, the star is going to be nice. I don't expect for them to show you a pedigree without carriers. If you're dealing with a recessive disorder, they'll show carriers. I'm not going to expect you to figure that out. Okay. All right, are there any questions then about autosomal recessive? Okay. What I'm going to do then is I'm going to give you 3 minutes, and I want you to tell me in the chat box if this is dominant or recessive. So again, I'm going to give you 3 minutes. In the chat box, let me know dominant or recessive and tell me why. All right, your time starts now. 3 minutes. And I will put on some music, but I'm going to get a copyright strike if I do. Let me see if I can find some non-copyright music.
Stream 85 plus live channels with no hidden fees. YouTube TV. Try it free.
Good grammar and
Many
spelling.
commercials.
But if you want to write essays that inspire.
Oh, there you go. It's nice and relaxing. I don't super understand the sci-fi scene we're looking at, but it's cool.
It's future Wally.
It looks like, my mind, I don't know, I guess you guys probably never seen this movie. It's a movie called Elysium. In Elysium, there's like, it's like a rich-poor kind of thing. So the really rich people live, you know, like in satellites above the Earth. And all the really poor people live on Earth. And so on Earth, it's like this post-apocalyptic wasteland. You know, everybody has cancer. They're all dying because the Earth is poison. And then all the rich people up in the sky have all this really fancy technology and they can cure cancer or whatever. And so, of course, it turns into a big class struggle with the people on Earth uprising against the people in the clouds. So this is like a really nice version of that. You see this common person looking up at the rich people in their bubble as they zoom past on their starships. But this guy, I guess, is content because he knows the revolution is coming, and soon those aristocrats will pay for all their misdeeds. But that's what I see when I look at this. Maybe you see something else. About 40 seconds left. And so you see these giant tubes connecting the Earth to the city. They're draining the Earth of its resources, and they're pumping it all into their fancy apartments. Can you believe it? Can you believe that they would abuse the common folk like that? Even in the Wall-E future, the robots have taken over. I guess that'd be more fun, huh? I guess it'd be more fun if it wasn't necessarily rich and poor, but it's like the robots are living better lives than the people. That'd be kind of fun. And time. Okay. So enough of that dystopian future. Let's get back to our class kick. So, dominant or recessive? Again, in the chat box, let me know what you think. I will say that you can look at this for about 5 seconds and figure out if this is a dominant or recessive trait based off of just looking at the pedigree itself. Hey, Brighton was listening. Very good, Brighton. It would be recessive because dominant doesn't have carriers, right? Very good, Zarya. Very good, Josiah, right? We see all these carriers. There's a carrier here, carrier here. So that means we're dealing with a recessive trait. Now, I did this the other day and it really confused me because everything works out fine. Like if you do this family, it works. If you do this family, it works. The blue is like this. The red is like that. And then, of course, the carriers are that. The only thing it doesn't work for is this down here. And this is what confused me, was this right there. Now, I finally tracked down the source for this image, And their explanation is that, Punnett squares represent probabilities. And because of that, you're not necessarily going to always be getting what you expect. So, I mean, that seems like kind of a weak answer to me. But that was the answer that was given. But what we're going to do is we're just going to ignore those. Pretend like those don't exist, and let's go ahead and do some Punnett squares. So let's say that we're going to tackle just the easiest one. This one right here. Right? So we go ahead and draw a Punnett square. We know that mom and dad are both heterozygous. So we got big A, little a, big A, little a. You do your cross, and what you figure out is that your kids are going to be homozygous dominant, heterozygote, or homozygous recessive. And what you notice with the kids is we've got here, I guess I should make it smaller, and maybe make it white. We have our homozygous dominant. We have again our homozygous dominant. We have our heterozygote here because it's a carrier. And here we have our homozygous recessive. Now, let's focus on this cross. Let me use green with this one. Oops. Woohoo. There we go. It feels like it would be so much easier to do this on a keypad, and yet it's so hard. Okay, so we know that mom is going to be homozygous dominant. Right, she's going to have two capital letters, so she's going to have big A, big A. We know that dad is going to be a heterozygote, right, because he has those shades. So we got big A, little a. You do your thing on the inside, and you find out that your possible alleles are going to be that, 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 that. And that's what you notice. You have no affected offspring, but you do have heterozygote and homozygous dominant. Same thing with this one. Homozygous dominant cross the homozygous dominant. We're going to have all homozygous dominant kids. All right. So thankfully, the star's not going to throw anything quite like this at you. Like they're not going to have parts that you ignore. But because we did our Punnett squares, you could probably even do one more, like I said, for this one. But we did that one, everything else works fine. Even this one works to some extent. You have a homozygous dominant cross with a homozygous recessive, and you get carrier kids. So they all kind of work. Okay, so are there any questions about predicting dominant or recessive alleles in pedigrees? Because we're pretty much going to leave it at that. We're going to talk about sex-linked probably next week, but sex-linked is pretty advanced, and I don't expect to start to do a whole lot on it. I think it bears mentioning, but I don't think that we're going to do as much practice that we've done with Punnett squares and pedigrees with the sex-linked traits. Okay, then let's go ahead and focus back on our incomplete dominance that we were talking about yesterday. So remember that when we're talking about incomplete dominance, we're talking about a dominant allele that is not totally dominant, hence incomplete, right? So in snapdragons, flower color is controlled by incomplete dominance. The allele for red is capital R, the allele for white is little r. Knowing this trait is incomplete dominant, what would the phenotype be? So like we said yesterday, whenever you're blending these two things together, what would you expect to see? So if you're mixing red and white, I would say that you're probably going to be expecting pink. So that would be the heterozygous color. Thank you, Josiah. Very good. Now, it could be purple, but pink is probably going to be the more reasonable answer. Now, remember that pink is going to be the heterozygote genotype. So if we're talking about red, that's going to be the homozygous dominant genotype. If we're talking about white, that's going to be the homozygous recessive genotype, because the heterozygote, again, is going to be the pink. Now, a pink flower snapdragon is crossed with a white flowered snapdragon. So looking up at part B, you see that the red is, I'm sorry, it says pink, a pink flower snapdragon. So yeah, the heterozygote is crossed with a white flowered snapdragon. So you have big R little r crossed with little r little r. Get a little bit closer. What are the expected probabilities? So you run through your Punnett square. You got big R little r, little r little r, big R little r, little r, little r. So what does that mean? You have 50% big R little r, which are going to be pink. You have 50% little r, which is going to be white. Now, if you're giving a ratio, you're just counting stuff. So if you're counting, there are two big R little r's for every two little r's. So the way of saying that would be 2, 2. But this can be reduced down. So for every one pink, you have one white. There you go. Now, I don't expect to see ratios on the star. It's not super common, but just in case, it's really just simple as counting. 2 to 2, which again reduced down to 1 to 1. So for every one pink flower, you'll have one white flower. Again, probability-wise, not necessarily in reality. Still pretty easy, right? Edward is extremely romantic and wants to give Bella an entire bouquet of pink snapdragons, her favorite flower. Unfortunately, Edward only has red snapdragons in his greenhouse. In order to produce the most number of pink snapdragons, what color flower should Edward cross with his red snapdragons? Show the Punnett square to defend your answer. So this guy's got red flowers. We know that from the last problem is going to be homozygous dominant. Now, if we're trying to figure out then how to get the pink snapdragons, remember that pink is going to be the heterozygote genotype. So he's trying to get to the heterozygote. We have homozygous recessive. So let's say then that he needs at least one of those, right? And ideally, he would want to have all of them, right? It says most number of pink snapdragons. So let's say that he needs to have all these be pink. In that case, you can work backwards, and you get your other genotype. You have your big R here, little r there, big R here, little r there. He would need to have a white flower to cross to get 100% pink snapdragons. So this cross should produce 100% pink snapdragons by crossing with a white flower. There you go. So the way to get to 100% would be by crossing the red flowers with white flowers. Now, what would his second choice be? Let's say that he doesn't have access to white flowers. So he still has his red flowers. So you go big R, big R. If he doesn't have access to white, then hypothetically what he could do is he could cross them with other pink snapdragons. Now, this is not going to give him 100%, right? This is going to give him big R, big R, big R, bigger. Those are both red. And then here, these are both pink. So this would give him 50% pink snapdragons. Now, again, in this universe, Edward should probably just give Bella the pink snapdragons that he would use to cross. But, you know, for the sake of filling this out, we'll just say that. Very good. Thank you, Josiah. Okay. Now, last but not least, I wanted to introduce this because the star could do it this way. I don't like it when it does this, but I don't want to say it's done to intentionally confuse you. It's just trying to prepare students who go forward with genetics. Now, like you saw with the snapdragons, we had the capital letter, the lowercase letter, right? Dominant, recessive. Here, if we're dealing with different letters, normally we'd be talking about dihybrids, which again we'll get to next week. But this is actually an incomplete dominance question. Now, hair color and certain breeds of horses can be brown, white, or palomino. Now, when it asks you about what type of inheritance pattern this is, we're looking at a blending of traits, right? Palomino is a blending of traits, which means incomplete dominance. Now, since it's incomplete dominance, you're still dealing with, these alleles. But we're not dealing with two different alleles. It's going to be the same allele. They're just represented differently. So we have certain breeds of horses can be brown, white, or palomino. Brown is represented with a capital B, and instead of white being represented with a lowercase b, it is represented with a white. With a capital W. So a whole different letter. But again, we're not dealing with two different traits. We're still dealing with hair color. So it's still just the one trait. And palomino is going to be the resulting heterozygote genotype, which is big B, big W. So if we are crossing a brown horse, so brown again is going to be capital B. So capital B, that's going to be our brown allele. Our white allele, or genotype, I guess, WW, and then palomino is when you got two of them together. So see how it's kind of like our dominant recessive? So the palomino is the heterozygote, right? It's got the capital lowercase. Here it has the two letters. So I don't love that it does it this way, but that's just, sometimes you might see it that way. So show that a cross between a brown horse and a palomino horse. There we go. Those are our two genotypes. So you cross them. You have big B, big B, big B, big B, big B, big W, big B, big W. So remember that big B is going to be brown, whereas big B, big W is going to be palomino. So what does that mean? It means 50% big B, which is brown, 50% big B, big W, which is palomino. So it's very similar to what you've seen before with our dominant recessive. It's just represented a little bit differently. So again, don't be confused. We're not dealing with two different traits, right? We're not dealing with those 16 possible outcomes. We're still just dealing with brown, white, or palomino. And just like last time, we have 50-50, which means we have a 1-to-1 ratio. Now, like we saw with yesterday, I don't like using the word purebred, but all that means is that it has the same alleles. So no palominos are hybrids. right? Because they're both of those letters. So Palomino horses are worth a great deal of money. Which color horses would you breed if you wanted to produce the most number of Palominos? So just like we're trying to make those flowers, we're doing the same thing here. We're showing that we want the most number of heterozygotes, but this heterozygote is going to be letters. Again, it's a little confusing, and I know, I'm sorry, but what they're trying to show you is that we're setting up the possibility of what's called codominance, which we'll talk about tomorrow. But these are set up the exact same way that we've done these before. The only difference is instead of having a lowercase letter, you have two uppercase letters. All right. And there we go. Okay, so if incomplete dominance is still a little bit confusing, we are covering this again tomorrow with codominance. We're going to kind of compare and contrast the two, because codominance is not simpler, but there's a lot more. The examples of codominance I can pick pretty easily. Okay, so I'm going to shut up. We're going to talk. We're not going to talk. We're going to do our exit ticket now. I'll go ahead and stop recording. Oh, yes, that's what I get for talking so much. I'm glad you understand it then, right? So we would have a, go ahead and write it down just to make sure that we're doing this right. We would have a brown cross with a white, and that would give us the most Palomino horses. Good catch, Josiah. And that is worth 5 points on our next test. So congratulations, I will write that down. Whenever you catch me making my mistakes. Okay. All right. Fantastic work, you guys. Okay, so go ahead and start working on your exit ticket. I'll stop recording, and I'm glad that we caught that before I stopped.